Hello, Chem 101. Welcome to your first online problem session. You are going to be welcome to join me online in the future, but for the first one, I wanted to do a recorded one so I could edit out all my mistakes. Today, we're going to do a probably shorter version than your typical problem session. We're going to discuss the topics on the exam, which, as you may remember, is in a week from today, the 20th, as I'm recording. And so we'll discuss some new topics in class, but make sure you have time to study for Monday coming up. And then we will also review the homework. Typically, this will be done after you turn it in, but if you were brave enough to watch this before the first exam, or the homework is due, I should say, good for you. I'll help you out a little bit in case you have questions about that. So first I'll describe each of the topics on the exam, and then I'll do a couple examples from some of the topics, and then we'll do a couple of the parts of the questions for the homework, because you see they each have kind of a couple questions in there. And so hopefully by the end you feel a little more comfortable with some of the topics, and of course feel free to come find me in my office if you have questions at any time. So the exam is going to be broken down into 6 parts. Each part has a couple smaller questions in them, all based around the same idea. So the first part is going to be about physical and chemical change. And so already you're beginning to think about things like melting and freezing versus oxidation, for example. The second thing we're going to talk about on the exam are extensive and intensive properties. Extensive. And so here we're going to be talking again about either those additive qualities like mass and volume, which if you double the size you have more of, right? So something regarding the quantity. And then the other side, something that's intensive, a property of the state, like the temperature. If you cut your ice cream in half, it should still be the same temperature in each half. The third topic we're going to discuss on the exam are going to be units, right? We've talked a fair bit, not only about how they help you solve your problems, but also how, when we're familiar with them, it also helps standardize a lot of the work we do. So we'll discuss not just units, but also SI units, which again is the international system. I know it's reversed, that's because it's French. And this also the units we use as chemists, because there is a slight sort of disconnect at times. From there, we'll do some math. We'll talk about different conversions. On the first exam, we're going to be mostly concerned with density, a little bit with units, and let me see, a little bit with temperature as well. So some of these you probably worked with before in other courses. Shouldn't be too bad in this first exam, but if not, we'll do some calculations in just a moment. The fifth topic that is on the exam is going to be atomic structure. Obviously very important for chemistry, right? We want to know what all these chemicals are comprised of. And though we haven't covered this in the first week, we will touch on this early on this week, and we'll talk about the different components. And so I'll start you off here today with some of that. And then last but not least, we're going to talk about how we represent atoms on paper, right, with different symbols and how we can convey information about those, for example. And so this will be atomic numbers and mass numbers. Woo. And so I would say that this 1 through 4 has already been covered in class the first week, and these last 2 we'll touch on early on so that, again, you have some time to work through those and go through there. And we find that the homework, right, there was maybe a question or 2 that we hadn't covered yet. I'll do some today, and we'll also do some in class soon. So hopefully it's not so bad. And gosh forbid I don't cover something good enough for you. Again, feel free to go to YouTube or other resources where there's a lot of different people working through problems and such. You might find someone even better than me, possibly. Okay, so let's start with physical and chemical change. So this will be the first topic. Again, that's on our first exam. And again, it was really the first thing that we discussed in class. So hopefully some of it stuck. And so again, we know that matter, as we describe it, is comprised of mass that takes up space. We'll come up with a better definition at some point. Nevertheless, it can either sort of move around or actually change its composition. And so we're going to talk about these different physical and chemical changes. So one great thing you can do is literally create a line and just let's lump some of the physical and chemical changes on each side so we can begin to see the similarities between those. So I would argue that most woodworking, for example, is over on the physical side, right? Let's say that you're cutting a piece of wood in half. That's just going to be a physical change. So all these kind of mechanical motions of cutting or sawing and things like that are always going to be physical. We also have examples of, there are times that a color change will mean chemistry has happened, but let's say you're just painting, for example, your home. You say you're painting wood. There's no chemistry that's going on in this case, right? You're just adding one chemical onto another. There's no reaction that occurs. Though there may be some paints where that's the case, traditionally it doesn't in that way. Writing on the chalkboard, for example, is a physical change, right? I'm breaking up the chalk as I write. So you can also think about this with chalk or pencils, for example, right? That's graphite, not lead, that you're writing with when you write with those. Other good examples are when we begin to think about water or different transitions in the phase. So, right, we talked a little bit about the transitions between solids, liquids, and gases. And we know that going one to the other, be it melting or evaporating, or, for example, gases go to solids, that would be deposition. Any of these transitions, water is still water, nevertheless, we're going to have physical changes. So temperature, changes in temperature, can often elicit changes in the physical structure. It can also allow for chemical reactions too, as we'll see. And so we can see a couple of different physical changes here on the left. Now let's begin to think about our chemical changes. So these are going to be things that typically you don't want to happen to the things in your everyday life. For example, if you have milk in the fridge, even though it might freeze, like a chemical change, you can just thaw it and drink it again. But nevertheless, if the milk is spoiling, that could be because of either bacteria or just the fats that are in the milk. Over time, you're going to get a chemical change and then probably not want to drink that milk, for example. We have a lot of different metals in our world that do something called oxidation. So metals can oxidize, where essentially you're going to be adding, this isn't a perfect reaction here, but you're adding oxygen to your metal. And so it could crumble, the properties could begin to change. Often these oxides conduct differently than the metals themselves. And so let's say, again, you're building structures with steel. You're going to want to make sure perhaps that it's stainless, for example, and may not rust very quickly. So oxidation is a big one. On that same note, we can also think about combustion. Right? So we can think about really any type of fuel. This could be something like candle wax. This could be gasoline. This could be paper, for example. Right? So something with carbon, as we'll get to. So burning, which is really another word for combustion, are going to be examples of chemical changes, right? And the thing that's tough about these is it's hard to really go backwards. And yet with physical changes, well, perhaps you could glue it together, but melting, freezing, all that kind of stuff, you can do pretty reversibly and easily in that way. So you have to be careful when you get to a chemical change, because sometimes it's hard to go back. So that's just kind of a quick breakdown. Some of these may be familiar to you. Some of these ideas on the chemical side may be relatively new. The good news is we'll touch on all of these as we go as well. And so let's move to our second topic, but actually leave a line. We're going to talk quickly again about extensive and intensive properties. So I guess this is number 2. So again, always good to think about what these words are referring to. So these are properties of matter. So when we think about the units we're using to study things, kilograms, meters, they're studying properties like mass and length. And so these intensive and extensive qualities are going to be useful to help us distinguish those, to make sure we're studying the right thing, for example. So extensive quantities, as we've discussed, really measure size, or the amount that you have. Whereas the intensive properties are going to measure a quality, or really like the state that it's in. Right? So we can maybe think about the difference between you feeling full, having eaten a lot of food, right? There's a lot of food in you versus the feeling that you have. One is a state, you feel good. One is the amount of food that's in you. They're related, but they're not the same thing. So yeah, let's do a couple examples here. The easiest way I find is when you're given a property, think about whether if you cut something in half, that would actually change it. If you cut it in half and it changes, it's going to be extensive or additive, again, as we say. If you're adding it together, it will also change. Versus the intensive, where if you cut it in half, it won't matter at all. So let's actually start over here with color. Right? If I were to break this piece of orange chalk in half, it would still be orange on each side. I won't do that, but nevertheless, we find that the color is going to be the same regardless of how much chalk you have in this case. We also talked about things like conductivity. Right? Let's say you're an electrical engineer and you're cutting up wires. You hope that it's as conductive before and after you cut it in half. Similarly, what we find is temperature is going to fit on our list here. Temperature. And the great thing about this is, I guess if you cut an ice cube in half, it's still as cold on either side, as we kind of discussed. And so we can begin to see, right, similarities between these ideas that are going to be the same for, let's say bronze's conductivity will be the same regardless of where it is, but you might have different amounts of bronze in terms of extensive. So let's think again about things like mass. We can think about things like length. We can think about things like, right, if length is going to be measured in meters, we also have things like volume, which are going to be cubic meters. And so we can see similarities between these. And the big one that we're going to come to discuss more and more is going to be energy, which you sometimes might think of as the same as temperature, right? Like if I cut myself in half, which I wouldn't do, I would still have roughly the same amount of energy on each side. But what we find in chemistry is energy is quantized or in sort of bundles. And so if you cut something in half, it has half as much energy on each side. And just for fun, we can see that the units are somewhat similar to the ones we've seen before. But then we also have a factor relating to time, which we'll discuss in length as we go. And so feel free to look through some of the other sort of properties that we'll talk about in class, right? All of the units we've talked about relate to a property, and you can sort of categorize them as we go left or right in that way. Okay, I think we're doing pretty good. I will say, if it wasn't clear, that the way that I'm discussing these topics is sort of the way that they'll be questioned as well. So for example, for classifying physical and chemical changes, you might be expected to choose between chemical or physical. Similarly with extensive and intensive properties. So we're talking kind of multiple choice like, right, where you're circling one answer. I might ask you, of course, to suggest a physical or chemical change. And so you might have to think a little creatively, but you don't have to go too far, right? Cutting something in half is a perfect example of a physical change, and combustion or burning anything, nuclear fuel, for example, would be a great example of a chemical change in that way. So let's move on to our third topic, which is going to be units. Conveniently, we've already begun to discuss some of those. So the first big idea was that there is sort of a standard system that we use. So we have the kilogram, we have the meter, we have the coulomb, we have the Kelvin, and we also have the second, as really the 5 big ones that we'll tackle in this class. We will also use the mole, which is an amount, and then there's another one in the standard set known as the candela, which isn't so useful for us here. Perhaps if you take more physics courses, this has to do with how intense light can be in certain ways. So again, we know that these measure inherently different things, right? This is that they're incommensurable, which is to say, right, you wouldn't go to your doctor and when they ask you how tall you are, say your answer in pounds or kilograms, right? That doesn't make much sense. And so we're going to think also, first of all, how these are related, or can be used sort of in different ways. But nevertheless, these are the units that are standardized throughout the world, and, oops, I should say length. Right, it's easy to confuse units and the properties they measure. We have Kelvin for temperature, and then we have for time. And so, again, these are the standards that in a perfect world we all would use all the time. Perhaps you have a family who lives overseas and they talk about things in meters or kilograms. But we also find that chemists use slightly different ones, so non-standard units, but still very useful or helpful. And that's because a lot of these are set kind of to the human scale. And so what I mean by that is most humans probably weigh something between 50 and 150 kilograms. We are about probably 1 to 2 meters tall. And we live in seconds, right? You can snap your fingers to the beat of a couple seconds. And yet atoms, as we'll come to discuss, are very tiny. And so length, for example, isn't a very good measure. And so the chemist's unit, which I'll put in the parentheses, is going to again be the angstrom. But it's no surprise that we actually define the angstrom in relation to meters, right? So this is where we start, and then chemists do a little bit of extra work. And so this is times 10 to the negative 10 meters, so a much smaller version of that meter that we saw. Similarly, chemists sometimes use something known as the atomic mass unit, which is going to be, oh gosh, it's something like 1.66 times 10 to the negative 27 kilogram, which we'll come to find is relatively related to the size of a proton, or one of the components of an atom. So we can see it's just easier to talk about matter on a small scale with these different units. Similarly, probably unsurprisingly, chemists prefer things like Celsius, perhaps because it's more similar to things like Fahrenheit, which we use day to day. But nevertheless, you want to just make sure that you're comfortable not only with what these units are, but with what they represent, and then also which are standard and which are not. So we've done a little bit of that here. You might finish it out with some of the other work you do. Okay. So let's go on to the fourth topic, which is going to be conversions. So we haven't done too much of this in class just yet, but what we'll find is it's really not so bad, at least the math that we're going to do. Well, I'll do some examples with the homework in just a minute, but we'll do the temperature conversion right now, just because you haven't seen that at least just yet. So the premise here is that we have three different popular measures for temperature, right? We have degrees Fahrenheit, which we use every day. When I left to come here this morning, it was around negative 19 degrees Fahrenheit. So what we'll do now is convert that first to Celsius and then to Kelvin. And this will be what we use at least mostly in this class. So we find that there's an equation, conveniently, which you don't need to memorize. I'm actually going to Google it right now to make sure that I'm not wrong as I speak to you. There are many things that I don't remember that I should, like how to spell Fahrenheit, for example. Okay, so it looks like we take the temperature in degrees Fahrenheit, we subtract 32. We'll come to see why this is important, right? We know that water freezes at 32 degrees Fahrenheit, so now we see we're sort of converting to the Celsius scale. Then we put this in brackets, and then we multiply it by 5/9. So why 5/9? It just happens to be the sort of blend between the two scales, right? You may remember that at Fahrenheit, water boils at 212 versus Celsius at 100. So there's that ratio between the two in that way. There's no reason why, if we didn't have a different scale, that we couldn't use a different factor in that way. So let's do a little bit of math. A little confusing, right? It's not negative 19 here. It was positive 19. You can see I'm getting a little mixed up between Celsius and Fahrenheit. Nevertheless, let's do some math, right? So we have 19 minus 32, still times that 5/9. So let's see. So 32 minus 19, this is how I would do it in my head, is going to be just 13, but it's negative here. You are more than welcome to do all of this on your calculator, though the more you do it, the more comfortable you'll be doing it sort of on your own. I'm going to double check my math to make sure that I don't do this one wrong, as I would suggest you do, especially if you're also doing it in your head as well. So we have negative 13 times 5 divided by 9. I really love putting this straight into Google. It does the math for you. And we get out an answer of 7.222 repeating. Again, in this class, we'll typically use 3 significant digits, though technically here you were only given 2, so 7.2 would be a good answer. And again, the last thing we're going to do whenever we do calculations is just stop and say, does this actually make sense? So we know, for example, that 19 degrees is below freezing of 32 in Fahrenheit. And then what we also find, there we go, is that this is below 0, which is freezing in Celsius as well. So importantly, I would also put my units here. And then we have one more step if we want to go all the way to Kelvin, right? So let's do this maybe just up here in this little box. So we have negative 7.22 degrees Celsius. Kelvin is going to be equal to Celsius plus 273 degrees Celsius. I guess we'll keep the units the same. And so we can see here that we just need to add 273, I should say minus 2 degrees C in that way. And so our answer for Kelvin in this case will be just that. So let's see, I'm going to try to be good. 273 minus 7 is 266.22, well, minus 0.22. So 265.78. Let's check that math. Again, I'm not ever going to tell you that I don't make mistakes, but I hope that I get a little better about doing this on the fly throughout this course. So 273 minus 7.22. Yes, 265.78. Again, in this course, we would really just want 3 significant figures. So really a proper answer for Celsius, we said, was negative 7.22 degrees C. And then for Kelvin, our proper answer really would be 265.78. But we're going to round, right, to those 3 sig figs. So this is above, halfway, above 5. And so we'll get 266 as our answer here. And Kelvin doesn't come with the degree symbol. Doesn't matter if you write it. So that's just a simple example of how we could go from a temperature that we use in the States to something that scientists use or people in other countries, and then also that scientists use there. And that is the 4th topic of conversions. I'm going to do a density problem in a moment, but know that that will show up in this section as well. We haven't done too much math just yet. Okay. So topic number 5, which I have already forgotten, is the atomic structure. So briefly put, it's kind of easy this early on. We know that we have some sort of center collection called the nucleus. We know that that is comprised of protons and neutrons. And then we know that in that space outside, we have this kind of cloud of electrons. And we know that electrons are very light, so they don't factor into the mass, at least significantly. And so the atomic mass, or the mass of this atom, is going to be the sum of the masses of the protons and the neutrons. The charge, on the other hand, doesn't relate to the neutrons, which are neutral, just the protons and electrons. And it's rather rare that you'll have protons coming in and out of the nucleus, so instead the way charge changes in an atom is going to be via electrons. So to kind of simplify this idea in some ways, I like to make a little chart. So we have symbols for each of the components, right? Protons are positive, neutrons are neutral, electrons are negative. And then we're going to have Kg and then C in this case. So this is going to be distinguishing how massive they are versus how charged they are. And so we'll start with charge. We know they have roughly a charge of 1, a charge of 1, and a charge of 0. And in this scale, I'm just going to make them relative to one another, so as if I divided by the masses, just to show sort of proportionally how big they are. So if the electron were to have a mass of 1, the neutron and the proton are about 1,800 times larger, so much, much larger. Usually if something is more than 1,000 times larger, it's several orders of magnitude larger, we call it, which is to say so much bigger that you probably don't have to worry about that. Like, for example, if you won $1,800 in the lottery, but lost $1 while you were, running back home with the stack of cash, you probably wouldn't worry so much. Whereas if you only won $1 and you lost that dollar, you'd probably be upset. So the neat thing, I will say, which I didn't get to talk about much yet in class, is that it's because of these differences and their motion that all of our universe exists. If all of these were equal, we wouldn't get anything interesting, right? Just like the world's a fascinating place because people are different. Elements and atoms are interesting because of the different properties of what makes them up, and then as we'll find, how atoms also sort of bond together in that way. So a couple things, again, we can see that the charges are equal here, the masses are equal here, but there are, of course, differences as we go. A very good question would be, why don't we have another important measure here of, for example, size? Something to think about. And so lastly, right, as you can tell, these are models for how atoms actually are, and in reality, they don't actually seem like bowling balls or anything like that. So now we'll talk a little bit about how we represent them on paper, and you'll become more familiar with the types of things that we're working with. So the sixth topic is going to be atomic numbers and mass numbers. Sometimes we also call it atomic symbols. And so, again, there aren't periodic tables in all of these rooms. It's frustrating. You will have one for every exam, just so you know. So essentially what we do is re-represent all the different elements by a letter, or maybe 2 letters, or 3 actually sometimes, but essentially like a nickname. You've probably seen examples where people spell out different words with different elements, and it's usually funny or cute. But nevertheless, X here is just a placeholder. There is no element that's just X, though there is one that's xenon. So maybe we'll start with that as our example. And what happens is when we write these out, we're going to give 2 very important numbers in the subscript and the superscript that describe some of that mass that we were talking about before, but also allow you to calculate charge as well. So the first thing we're going to find is that the mass number is written up top, and the mass number is going to be equal to the protons plus the neutrons, right? All that massive stuff. And so if you need to know how much an atom weighs, you can just look at this number here. The other thing we can look at on the bottom is going to be known as the atomic number. As we will find, elements have different isotopes. Perhaps you've heard about carbon-14 being used to date different artifacts and things, versus carbon-12, which is most of what we're made of. And so that's going to be due to the differences in neutrons. And so one of the ways we standardize the elements and define them is by their atomic number. So when you look at the periodic table and you look 1 all the way up to 115 or so, each number is different and element is different, and the symbol would be different as well. So it's, I guess, perhaps a little redundant that you have a number and letter symbol because this would imply that this number is fixed. So this is going to be the number of protons. And so something you'll see missing from these symbols is the number of electrons. And so one of the things we do is we assume, at least to start, that our atoms are always going to be neutral, and so that positive and negative charge balances. And so we're left with, if we know the number of protons from the atomic number, we would assume that there are that many number of electrons as well. So from this, we can get to the number of electrons that we talked about. Now again, electrons are going to be probably one of the first things to be shed from an atom, though neutrons and protons can come out. And so, for example, if I tell you that this element has a charge of +2, we know that 2 of these electrons have left to leave that higher proton number than electron number. So it's kind of all about this balance, as we'll find. And we'll be doing a lot of counting to make sure that things are balanced as we go. And so let's just do a simple example. I'm going to just make up something for fun. Let's see, there was, if you ever watched Avatar, not The Last Airbender, but that one with the blue people, there was something known as unobtainium, which that's not a real symbol, but we'll make it up. So if I just write, let's say there's 37 here and 102 here, a couple questions I could ask you are, how many neutrons are there in this made-up atom? And so we know that the mass number is protons plus neutrons, and the atomic number is just protons. So, for example, number of neutrons is going to be equal to 102 minus 37, or again, this is the mass number minus the atomic number. Right, so we can see how even with very little information, we can actually pull out a lot of ideas. Similarly, if I ask you how many protons, how many electrons are in a neutral atom of unobtainium, well, and obviously this couldn't be real. It should be like 1/3. Anyway, how many electrons are in a neutral atom of unobtainium? We would say that, well, since there are 37 protons, there must be 37 electrons as well. And so again, we can see that there's quite a lot stored in here. What I was quibbling about before was clearly there is an element that's 37, so I should have made it really high or something like that. If you're interested in kind of learning more about why there are only a certain number of atoms or why certain atoms are reactive or nuclear in some ways, I would Google the island of stability. It's a really fascinating concept. Where people hypothesize about what other atoms may be stable even beyond radioactive ones. So think about that. Okay, so that's a pretty fair review of the things that will be on the first exam. You will note that there are things that we discussed in class that may not make it on this first exam. We may still use them later on, but they won't be directly tested, at least right away. So you should feel comfortable, if you feel comfortable with all of that, taking the exam on Monday. Okay, so now that we're done with the review, let's talk a little bit about these problems. Hopefully they weren't too bad. So yeah, let's just talk about them. They, of course, relate to what we've just been discussing. So we talked, I'll just choose one from each, and then we'll kind of go from there. So, right, we were looking just a moment ago. This is question 1. This is the second part. Kernels of popcorn are heated to make popcorn. This is going to be a physical change. I actually got to do a really neat lab when I was in high school where we measured the pressure and volume change of popping kernels. And again, here we have temperature being applied, right? You're heating it up. That's what microwaves do. And so we get really just an explosion, but not a combustion or anything like that. For question 2, for example, we have a variety of different units, right, with different prefixes. We talked a little bit about those. So ordering them from, I always have to write it smallest to largest, and giving examples of each of these as we go. Yeah, this way. Let's see, we have to start, the picometer at 10 to the negative 12. This is the size of atoms, right? We'll talk about bond lengths, right? The lengths between two atoms in a molecule or material. And so this is the scale that it's on. Very, very small, really incomprehensible to us. We also then have something like the nanometer, which is 10 to the negative 9. Nano is on the scale of many atoms put together, right? This is the kind of cool technology people are creating, and so you need at least a couple of atoms to make up nanotechnology. Hopefully we can make robots that are almost atomic scale, but still do cool things like deliver drugs or do surgeries, who knows. Next we have the micrometer. So this is on the scale of small living things. So we're talking cells, single-celled organisms, but we've gone from this kind of atomic world to the molecular world to now this kind of simple living world in that way. Next we also have, let's see, the meter, right? Yeah. Which is really just 10 to the 1. And again, if you ever need to know how big a meter is, door handles on a door are about a meter high, so it gives you a sense. And yeah, basketball players are probably over 2 meters. That's a guess. And then last but not least, you can see. We have the kilometer. It's not called a kilometer for whatever reason. And yeah, this is going to be distances that you would run, right? Maybe do a 5K, a 10K, things like that. Kilometers are going to be larger than the size of most buildings. They're going to be maybe the size of small hills, for example. And then you get slightly larger and larger things. Trying to think, the diameter of the Earth, something like 6,000 kilometers. So already several orders of magnitude larger, right? So the kilometer, or how far you run, is insignificant to the scale of the Earth, I guess, unless you run a lot. Okay, so that's for number 2. For number 3, we actually did a pretty good conversion just a moment ago, so I will leave you to try this one on your own, as you should. Let's do one of the calculations. Somebody actually emailed asking about the third one, which I will write here, about whether they had to do a unit conversion. So we'll discuss that in 1 second. 430 plus 0.039 grams. They should both be grams. See, even I forget units. Divided by 14.83 milliliter minus 6.92 milliliter. So the first thing I hope I don't have to review, but I'm happy to, is the order of operations, right? You want to make sure that you're not just going left to right? You wouldn't add this and then divide by this number. We want to make sure we're doing the math in each of the parentheses together. I'm trying to see if I can do this in my head. I probably don't want to. I'm going to type it in Google. So you obviously won't have phones in class, but you will have calculators. And even if you think you can do the math in your head, double check it. Never hurts. So all I'm putting in here is the first one, right? 7.430 plus 0, that's the letter O, 0.039. Great. So we can see here what I was getting at was you have a relatively large number and a relatively small number, right? So how will that affect with significant figures? The thing we'll do at first, at least while we're doing the math, is keep them all, and then we'll round at the end. So here we get 7.469. So we'll hold that. That's how many grams were measured, whatever this is in reference to. Then we'll do this other set of parentheses, and then we'll divide the two together. So here, I'm going to put it in again. So we have 14.83 minus 6.92 0.92. We have 7.91 milliliters, right? And technically, we would have another digit of significance, at least for now. Not going to be there in the end anyway. And so we can do just this final calculation conveniently. We have 4 significant digits and 4, so we'll be left with 4 before you round and give me 3, because that's how we do it in this class. Okay, so we have 7.469 divided by 7.91. I can put the 0 in, it doesn't matter. Before I show you the answer, I want to invite you to think about what it might be. One of the things you'll always do when you look at your answers before you turn them in to me are double check to make sure they're reasonable, right? Because it's so easy to mispress a button or to have done math wrong somewhere. And so densities, you may not be familiar with all of them, but water is a good standard. That's going to be 1 gram per milliliter. And so we would expect them to be somewhat related to that, maybe 10 times that or less than 10 times that, just as sort of a range. And here we have a density of 0.94447, and then it goes on. We know that technically we only have 4 significant digits because of the numbers here. And then we also are kind of in this class always stick to 3, which is more than enough in that way. The other thing we'll do, grams per milliliters, put in our units. And we'll also just stop and again see, okay, this is pretty close to that of water. Seems like a reasonable thing for a chemical. It's not a million, it's not really tiny like on the pico scale. And so this is probably a good guess. A fun extra question is, if you were to mix whatever this is with water, would it float or would it sink? And we can see here, because the density is less than water, it would float in that way. So this might be oil, this might be something organic, might be you. Maybe this is your density, I don't know. And so that's going to cover actually really the last question as well, right? You're just taking that mass and dividing by that volume in that way. I will say there are times that density questions use somewhat confusing units. So one thing to always remember, at least with density, is that 1 centimeter cubed is going to be equal to 1 milliliter. Again, still both measures of volume, but we have a single unit for it, the liter, versus a derived unit, which is to say it's made up of many meters or cubed in that way. The other secret trick I will teach you, because you've watched all the way to the end, is the density triangle. Woo! I'm going to try to get this right. So we know that mass over volume equals density, and we'll check those units, right? We have kilograms divided by meters cubed equals kilograms divided by meters cubed, right? Once you write it out with the units, it looks kind of obvious, right? It looks silly that I even wrote that. But up here, it may look a little more confusing. Nevertheless, what we find is if we put mass, volume, and density in our triangle, you can always remember how to do these calculations. So look, for example, if you want density, you cover it up, you divide mass by volume. That's really hard to see. So if I cover density, what I want, mass divided by volume. Let's say now I'm torturing you with the question and I give you the volume and the density, but I want the mass. You just cover the mass and now it's density times volume. And so this is just a fun little trick. If you're playing with units though, you don't even really need it. But we can see again, right, we wanted mass, so we multiply this over. So that's just kind of a fun way to help you out if you're a little stuck. That's it. We did the first one. Hopefully in the upcoming sessions, you guys will join in, ask questions. Otherwise, I will see you all this week, and good luck on the first exam.